Here we will look into another abstraction which is important for linear algebra. This time we will be generalizing definition of scalars, of real numbers. Real numbers were just the base of all the things we did in linear algebra. And if we look back at what we needed from them, we wanted to have arithmetic working seamlessly. So fields are axiomatizations of numerical systems where only arithmetic is possible. This is not a definition, but just an informal description. So complete is not in mathematical sense at all, but just in the common sense. Full or complete arithmetic is possible in what is going to be a field, meaning that we can add things, subtract, multiply, and divide by non-zero numbers. Well, generally speaking, they don't have to be really numbers, but most of the first examples of fields are numbers. But first of all, what is a field mathematically? Well, it is a set together with arithmetic operations. And definitions are long enough even without listing only four operations. So what people noticed is that subtraction is really something about division. Sorry, it's about addition, and division is something about multiplication. It's sort of special property of multiplication. It can be reduced to statements which are effectively multiplicative. So that's what we will be doing as well. We will be really axiomatizing just two operations of addition and multiplication. And each of them is what's called a binary operation. It takes a pair of elements, numbers in special cases, and produces the third one, which is called the sum or product in these two cases. So usually we denote the sum by plus and the product of the two by putting them next to each other, or perhaps inserting the symbol of that operation, a dot. These two operations have to satisfy conditions. Conditions just for them, and conditions bringing us subtraction and division. So the first condition for addition is associativity. If we have three elements and we want to add them, doesn't matter which pair we add first and then which third we add after, the result has to be the same. We also want to have commutativity for addition. Which makes the same answer for a pair of vectors and a pair taken in opposite order. And then we should have something which would prepare us for subtraction. So subtraction is really an addition, but with addition with negative, with the negative elements or negative number. To make sense of negative, we first have to make sense of the zero number. So there's a special element, its special properties that when we add it, the special properties in terms of addition only, when we add it with anything else, the result will be that second summand. So that is the zero axiom. I will write it here. And then the last, what gives us subtraction, is that for any number we should have, and that is a symbol that there exists. So that is any, that is a upside down, that is there is or exists. A number which is called negative x, and again the thing which makes this number negative x is the following property, that when we add it to x, the result will be that zero. And because of commutativity, we have it the other way as well. So that is all for addition. For multiplication, we also have associativity. And commutativity. In place of 0, we should have a special number called 1. Its special property is that when we multiply with 1, anything at all, the result will be that something. And finally, we should have division for non-zero. So we assume that x is non-zero number in our field, then there should exist x inverse, its inverse, which we make sense by these two equations. Again, one is enough because of commutativity, the other one will come for free. So finally, the two conditions which will link the two operations together, they're called distributivity conditions. So this is again associativity, but for multiplication. Commutativity for multiplication, one axiom and inverse. So here's negative, negation or negative, and here's inverse or division. And the last two distributivity axioms are like that. And one is enough because of commutativity, the other one will become redundant, but I will write it anyway. Of course, these are all very familiar, very natural for us, because they most of the axioms are true for addition and multiplication of numbers without any conditions, so like natural numbers. When we multiply them, when we add them, we have associativity and commutativity, and depending on what you mean by natural numbers, you might even have 0. When we multiply natural numbers, you will have associativity and commutativity, and definitely 1. What we won't have in natural numbers is negatives and inverses. So natural number system is a good system, but it will have only in general two operations of addition and multiplication. It will lack subtraction and division for arbitrary natural numbers, so it is not a field. I'll put a cross here just to represent this fact. The next set of numbers we're usually dealing with are integers. And integers to natural numbers is as if we just wanted to have subtraction. And adding negatives is what makes integers out of natural numbers, but still we don't have inverses, so it is not a field, although a good arithmetic system. To make a field, we have to add inverses to integers, and this set of numbers are called rational numbers. And this is our first example of a field, the simplest field, really, in essence. Then, there are many things in between, but next in sort of short story will be real numbers. what we add to rationals to get reals are sort of all the holes in the line on which rational numbers are written. So all the numbers in between any two rational numbers, just to be able to measure length. So that mathematically is done through usually limiting processes, Cauchy sequences, but can be also done algebraically through Dedekind cuts. But I'm not here defining real numbers, I'm just using them as the most sort of standard example of a field, of a domain, arithmetical domain for linear algebra. And that is still sometimes not enough, like for solving polynomial equations, real numbers are too small. If we want to add solutions of all polynomial equations, we will end up with what are called complex numbers. And they still be a field, they still be having all four arithmetic operations possible. These are sort of all in the same way numerical examples. There are more interesting depending on what your interests are. There are different examples. So the easiest of non-numerical would be something coming from modular arithmetic. It's again not going to be defined here, just mentioned with the simplest case presented. But the idea is we identify integers if they have the same remainder. We look at really remainders of integers modulo some number, and if this number is a prime, the resulting arithmetic system will give us a field. So the easiest prime will be 2, and the resulting set of numbers will be are naturally called binary numbers, or really binary arithmetic, because binary numbers are something else, but okay, I will use this term. So the set of remainders is just of two elements, remainder 0 for even numbers, and for odd numbers we have remainder 1. And then the arithmetic operations are just as if we are taking the numbers and adding them and looking at the remainder. So if we add 0 and 1, just tabulate the answers, we will have, of course, when we add 0, we will have the same number as the other sum, and we'll have 1 with itself added to itself. The result will be 2, but its remainder, it will be even, its remainder will be 0. So that is the complete addition table. Complete multiplication table is even easier to fill. 0 multiplies with everything, giving us 0. 1 with 1 is 1. So that is a weird example, but still fitting all the requirements of a field. There is nothing to invert by 1, and of course 1 is its own inverse. So we can divide by non-zero number, we only have one such, and when we divide by it, we don't do anything. And yeah, the rest is also easy. So we can subtract. -1 is the same as 1 again. Both the additive and negative mirror image of 1 is just the same one. So that is it. See you later.